for being here. So we have the pleasure of having with us today Lindsay Schoenbohm. Lindsay is a professor at the University of Toronto, Mississauga, Canada. She explores climate tectonic interactions using primarily structural and geomorphic field-based mapping, but also dating and remote sensing. And today she will be sharing her results on the importance of considering lithological resistance to erosion in landscape evolution. So when you are ready, Lindsay.
Okay, well, thank you so much. And thank you everyone for coming today. There's some names that I'm seeing coming into the space I haven't talked to you in a long time. So I'm glad to see you here, that you came out to see what I have to say, and I hope to reconnect in person sometime soon. So I'm going to be talking about lithology and how it matters in landscape evolution. Before I get into that, though, I want to make sure that I acknowledge the people who did all of the work that I'll be presenting today. I seem to be at a career stage where the students are doing all of the heavy lifting, and I didn't want to wait until the end to acknowledge them. I want you to know who they are so you can match a name to a face as we go through the talk. So the first two are James McCarthy and Aaron Segrin. They worked in Northwest Argentina. They both graduated. James is now a farmer in Western Massachusetts, and Aaron is working for the BC government on the Fraser River watershed. And then the next students are all currently working with me. So Josh Wolpert's finishing up in the spring sometime. I think he's here today. Maurizio Barcelos Haag is working in Brazil, and he's finishing up maybe at the end of the summer. And then Himani Yadav just flew into Bern today to work on some of her samples with Naki Akar, and she's working in the Canadian Rockies. So she may or may not join. Later on, if there's questions, I may actually throw it to some of these students because they'll be able to answer it better than I can. So I'm going to be talking about understanding the impact of tectonics and climate on the landscape. This is something that we've all been debating as a community for a long time, and trying to answer the question about what is the dominant control. And here's some headlines from groups that dominantly came down on the side of the importance of climate in driving landscape evolution, topographic metrics, erosion rates. And then here's some headlines. There's only 5 here, but it doesn't mean that the debate isn't equal, that came down on the side of tectonics as being the primary driver. And I'm going to try to tell you today that there's a few things that we're maybe not considering when we ask this question that we should be, that may allow us to ask this question in a more refined way, and that maybe it's not even sometimes the right question to be asking, and that things like spatial scale matter quite a bit. At larger spatial scales, we necessarily get a fuzzier view of what's going on. Because the resolution of the data that we're comparing to may be at different scales. And so it's important to remember which scale you're asking or addressing the question at. And the other thing I'm going to talk about a lot is rock strength. And so we all know from interacting with landscapes that rock resistance to erosion matters. We have slope forming units and we have cliff forming units. And so incorporating that into our understanding of landscape evolution is important. And this is something that I think has been getting increasing recognition in the last 10 or so years, both through modeling studies and field-based studies. So we're building on that work. And I think we're at a point where we can do some really interesting analysis at building lithology and real measurements of lithologic resistance to erosion into our analysis. So I'm going to be talking about 3 different field areas. We'll start in Northwest Argentina, and then move to the Himalaya, and then finish up in Brazil. And I'm also going to be introducing methods as we go along, sort of as needed, rather than all at the beginning, which would be kind of boring. So we're going to start in Northwest Argentina, the margin of the Puna Plateau here, where there's very strong precipitation gradients. There's also very significant lithologic differences across the region, and there's a lot of tectonic uplift. So it's a very dynamic area. So it's an interesting place to explore some of these interactions. But before I talk about that data, I wanted to talk just to make sure that we're all on the same page. Probably you are all familiar with this, but just to make sure we're on the same page around some of the methods we're using. KSN is going to show up repeatedly throughout this talk. So it's a measure of the steepness of a river channel, but it's corrected for upstream drainage area because channel steepness is going to vary based on the amount of discharge or precipitation, which is related to the upstream drainage area. So we want to get rid of that effect. And that allows us to see through to what else might be affecting and generating, for example, steeper channels. It might be generated by higher uplift rate, stronger lithology, or lower precipitation. So KSN is going to show up a lot. And another version of this is the specific stream power, which is corrected for upstream discharge and also involves looking at the channel width. So both of these metrics are a way of assessing how steep or not steep river channels are in the landscape. The other thing that we're going to be using throughout the talk is measuring erosion rates, and we're doing this using cosmogenic nuclides. So cosmic radiation strikes the surface of the Earth. It's dominantly high energy neutrons at the surface of the Earth, and it interacts with the rock.
Chat so we can see your.
So it interacts with the rock, and it dominantly interacts with rock in the top 3 meters of the surface of the Earth. And dominantly interacts with rocks in the top 3 meters of the Earth's surface through these spallation reactions. And it generates these geologically rare nuclides, things that we don't normally find on Earth. So if we find them, we know they've been generated by these interactions. And so we're going to talk about beryllium-10, which is generated in quartz. So there's a lot of creative ways that you can use cosmogenic nuclides because it's so sensitive to being located physically close to the surface of the Earth. But the way we're going to be using it is looking at integrated erosion rates across a basin. And the idea is that rather than going to 1,000 different locations within a basin and collecting rock samples and measuring erosion rate, we're actually going to allow nature to do the collection for us. And we're going to take sample from a point downstream in a watershed and assume that it's integrating material from upstream. So all of these individual sand grains are passing through this zone where they're accumulating cosmogenic nuclides. And then we're assuming that they're being transported rapidly downstream so that there's no additional accumulation during transport. So if the sand grains, the rocks are passing through this zone where they're accumulating nuclides, if they pass through this zone slowly, they spend a relatively large amount of time in that zone. And so they accumulated a large amount of beryllium-10. And if they pass through quickly, they end up spending less time accumulating nuclide. So if you have a high beryllium-10 concentration, it means you have slow erosion. And if you have a low beryllium-10 concentration, it means you have fast erosion. So we'll be using this to measure erosion rates in the landscape throughout the talk. So the first study I wanted to first area I want to talk about is Northwest Argentina, and I'm actually going to start with some work from Bodo Buchhagen, who I see is here today, and Manfred Strecker in 2012, where they looked at erosion rates on the southeast margin of the Puna Plateau. I'm just going to do a high-level summary of the paper, but this is an important figure showing mean annual rainfall in the background, so you can see the wetter foreland and the more arid Puna Plateau. And then cosmogenic basin-wide erosion rates are being shown here, both by the symbol size and the symbol color. And you can see right away that the larger symbols, the higher erosion rates are correlated with this wetter foreland, and you get lower erosion rates in the arid Puna Plateau. And here it is in a cross-section. This is topography from east to west, and here's precipitation from east to west, and you can see that where you have higher precipitation, you have higher erosion rates. Where you have lower precipitation, there's lower erosion rates, and the erosion rates and precipitation are extremely low here in the Puna Plateau. So at this scale of observation, it appears as though precipitation is the dominant driver of erosion rates in the landscape, and tectonics and lithology don't seem to play a role. So we wanted to, this was with James McCarthy, take a look at a smaller scale to see whether or not we got the same answer. So we've focused in on this part of the larger study area, this Calchaquis River catchment, where the precipitation is relatively uniform across the area. So here, if precipitation isn't varying, perhaps these other factors, tectonics and lithology, can come through and become more significant. So we used some data from the Buchhagen and Strecker study and added 5 additional data points. So here we're comparing erosion rates in this Calchaquis River catchment to, this is KSN, so that river steepness with red values implying a steeper channel relative to the drainage area. And then here's lithology and active faults on the right. So I'm going to tell you 3 short stories here. So the first one is this along strike variation in erosion rate. So we have lower erosion rate here. There's no significant difference in terms of the channel steepness, but there is a significant difference in terms of the lithology. So we have stronger rocks here, these crystalline rocks in this sort of gray-brown color, and then this sedimentary rocks in the green color here. So we think that in this case, erosion rate is reflecting a more resistant and a less resistant lithology. So erosion rate reflects lithology. Here's another example where we're holding lithology constants. We're looking at these resistant lithologic rocks across the basin. And we can see that there's a significant difference in erosion rates, so slower erosion rates and faster erosion rates that would not be explained by lithology. However, you can see that there's a significant difference in terms of the river steepness, and we're interpreting this as being the result of an active fault running right through the middle of the basin, such that you have higher uplift on the west side than on the east side. And so in this case, erosion rate and channel steepness are reflecting active faulting. And then a last example, because I can't ignore this little blue spot down here at the bottom where we have extremely low erosion rates. It turns out in this case that there are two normal faults that run through the region that drop down the hanging wall blocks here. And so that results in the low erosion rate, and lithology doesn't play a role, we don't think. So in this case, erosion rate and channel steepness are reflecting active faulting. So at this scale of observation, the regional scale of observation, it looks as though erosion rate and channel reflects precipitation. So climate is the dominant driver. But when we zoom in, we get a different result. At the basin scale, erosion rate and channels are reflecting faults in lithology. So tectonics and lithology is the dominant driver at this scale of observation. So this additional data that additional erosion rates that we had led my next student, Erin Segrin, to think in more detail whether we could treat this question in a more statistically robust way. And so that brings us to Erin's database. So she added a few additional samples to both James and Bodo's data set. And we ended up with about 64 different erosion rates in basins along the southeast margin of the plateau. And like I said, Erin was interested in the statistics and dove right into it and was able to come up with some a really interesting approach to this problem and some interesting results. So here's her erosion rates, or the assembled database. She compared these erosion rates, so she regressed them essentially against 9 different metrics. So there were 4 topographic metrics. So I'm showing local relief and the specific stream power. She also did a KSN regression and also looked at hillslope angle. And then she had 3 climate metrics, so precipitation and vegetation and DVI. She also looked at mean annual temperature. And then the last 2 regressors are lithology and tectonics. So for lithology, we had good geological maps, but we didn't have good rock strength data. So we ended up doing this logical but quite unsatisfying assignment. We just said rock strength varies between 1 and 5. Hard rocks are 5, and granite is a 5, and unconsolidated sedimentary rocks are a 1. So it's logical, but not very sophisticated. And then we approached tectonic activity by measuring mountain front sinuosity. So the idea is that a more active fault is going to have a straighter trace. A less active fault, erosion is going to degrade it. And so its trace is going to be more sinuous. So this is a measure of how active the faults are. It's also unsatisfying. I'll talk more about that later, but it's the best that we could do. So then she did regressions. And I think one of the really insightful things she did was she didn't just look at mean values. She actually looked at summary statistics. So she looked at regressions against mean and the median values, but also minimum 10%, 25%, 75, 90, and the maximum values. And then she also looked at ranges. So the interquartile range, that's 75 minus 25, and then the 90 minus 10. And she found that this is just a bivariate regression. She found that she got better results for values that captured more extreme variables, conditions within the basin, or that captured the ranges. So in this case, the interquartile range. So all of these topographic metrics had okay correlations, but better when you use these extreme values with her measured erosion rates. And then she did the same thing with the climate metrics. And again, found that extreme values like the maximum or the 90th minus the 10th gave better regressions. And in particular, we were really interested to see this NDVI come out as a significant regressor. It performed quite well just in a bivariate regression. I'll say a tiny bit more about it, but if you want to hear more, maybe ask during the questions, because I've got a lot to say on this, but it's sort of on a slightly different trajectory than the rest of the talk. So we couldn't do summary statistics for lithology or mountain front sinuosity because they're categorical values. So I don't have the same kind of pretty graph to show, but I can actually show all of it integrated into one plot, which will come up a bunch. So this is a regression of erosion rate versus these various metrics, and a perfect regression would give you this one-to-one line. And you can see here's NDVI in this red line doing okay, but here's lithology performing quite terribly. There's an R squared of 0.01, so it's really not a good regressor. And then tectonics in this purple line right here, so also not great. So why did lithology and tectonics not show up here? So is it because of our spatial scale of observation? Maybe when we zoom out, they don't matter. It could also be that we really haven't constrained those values well. Just doing this arbitrary assignment, 1 to 5, doesn't work great. Maybe SMF isn't really a good way to measure the tectonic activity. And then the third, that's probably is the case. And then the third possibility is that we just shouldn't be looking at this in a bivariate space. We really need to be doing a multiple regression, because all of these things probably play some role, and they interact with one another. So the next step in Erin's work was to do Bayesian modeling. So she used the best summary statistic variable from the bivariate regressions. So she didn't use a gazillion. She only used 9 different variables, and they were the best ones selected from the bivariate regressions. Ran 512 models, and she selected the 10 models with the best performance for further analysis. So of those 10 best models, there were 3 significant regressors in every single model, and in some models, they were the only significant regressors. So they included NDVI, which is not surprising. It did very well on its own. Also included specific stream power, and in particular this interquartile range. And then last, lithologic resistance actually showed up here. So the answer probably is that even though we weren't doing a great job of measuring it or quantifying it, looking at it in this multivariate space allowed the importance of lithologic resistance to come through. Interestingly, tectonics does not show up as a significant regressor. So again, it may be that we just haven't constrained it well, or it may be that it doesn't matter at this scale, or in general, who knows. Anyway, so again, if you want to ask more, the NDVI, we think it performs better than precipitation alone, perhaps because it essentially samples over a longer interval. A tree might be alive for a couple of 100 years, and it may integrate precipitation patterns over that time. And so that's really quite interesting. Another takeaway from her work is that it's better to look at summary statistics in these, not just rely on means. But again, lithologic resistance shows up in here, which is quite interesting. Okay, so now I'm going to transition to talking about the Himalaya, which is another part of the world where there's lots of tectonics, lots of strong precipitation gradients, and lots of interesting things going on. But before I get into that, just a brief pause to come back to methods. So I'll talk a little bit about the stream power incision model in a very basic way. Before we were looking at KSN, just empirically pulling it from the landscape, but the stream power incision model allows us to build a prediction between erosion rate, KSN, and this constant here called K. So we think that there's a relationship between channel steepness and erosion rate according to the stream power incision model. And this is, was introduced a long time ago. We've been using this relationship for a long time, and it's quite powerful. But the problem is K hides a multitude of sins. There's a whole bunch of stuff that gets rolled into K, climate, lithology, and also erosion processes. So perhaps it's not appropriate to have a single value there, and there may be a better way to treat it. And so Byron Adams published a couple of years ago some really important work pulling apart this relationship and taking a more sophisticated approach to looking at climate and lithology as separate factors. So the first version, I'm showing you 2 versions because they both show up in later analysis. So I have to tell you about both. But the first version of treating this in a more sophisticated way is this introduction of this idea of KSNQ. So KSN normalized for upstream drainage area essentially assumes that precipitation is uniform, but we know it's not, and we have good data now that allow us to actually correct for real precipitation in a watershed. So KSNQ is corrected for discharge by using precipitation data. So essentially you're pulling climate out of K, and so that gives you this new variable KLP, which still includes lithology and processes. So the other way of doing this is leaving KSN alone, but splitting K into KLP times rainfall to the power to M. So again, KLP shows up in both of these. So the next study in the Himalayas, they both use KSNQ. And then when we talk about Brazil, we'll be looking at this formulation down here. But both of these are just ways of separating out climate and lithology. All right. So Kellen Whipple and others just published a really interesting study in the Himalaya, and he's got these curved panels, so I couldn't just trim out the stuff that I wanted to show you, so you get all of it. But just if you want to focus down on this bottom panel on the left, panel D, this is their KQSN map for the Himalaya. So again, it's corrected for precipitation and showing channel steepness. And you can see these very steep channels just north of this high Himalayan topographic front, and then channel steepness decreases again as you get into Tibet. And then if you look at the bottom panel on the middle panel on the right, panel B, this is measured erosion rates. And when you first look at this, it's maybe a bit sparse, but it's not actually. This is a really impressive data set that now over many years we've generated as a community in the Himalaya, showing cosmogenic basin-wide measured erosion rates. And again, you can see them reflecting this high Himalaya topographic front with higher erosion rates north of it, and then dropping off again as you come into Tibet. So we can use, and they did in this study, channel steepness, KSNQ, regressed against erosion rate. And all of these colored dots are showing different precipitation bins. And the point they're making is actually if you correct for KSNQ, the different precipitation zones collapse into essentially this single regression right here in the dotted line. And that allows them to, so they use this equation, and by regressing measured erosion rates against KSNQ, they can solve for KLP and N. And they find that despite it being a heterogeneous region, they're able to come up with a single, quite convincing regression for the entire area. So now that we have measured erosion rates calculating KLP, you can then use KLP and KSNQ to predict erosion rates. And so that's what they've done in this bottom panel. These are predicted erosion rates based on this KLP value that they calculated, and the KSNQ that's measured. So okay, all right, sorry, my animations got ahead of me. The problem with this study, and the authors point this out, is that they weren't able to resolve for geologic factors. They just didn't have, this is a scale problem again, they didn't have sufficient resolution on their geological or lithologic data to build it into their analysis, so they didn't build it in. So enter this little yellow box down here, this part of the Himalaya where you can see that there's a data gap, so it'd be very nice to fill in some erosion rates here. And also it turns out there's a really excellent and detailed geological map that we can make use of that Pete DeSelles published just a couple of years ago. So this is work from a student, Josh Wolpart, which is in progress. So he did a similar analysis to Kellen Whipple's group. This is a KSNQ map for the Karnali watershed in western Nepal. Here's new erosion rate data. Some of this is unpublished from John Harvey, but most of this is Josh's data. And then here's the extracted geology for just this watershed. So here's Josh's version of that regression. So the gray dots and the gray line are Kellen Whipple's data. And these new symbols are his additional data from this Karnali watershed. But because of this geological map, he's able to separate out these watersheds based on their dominant lithology. So the symbols outlined in red are dominated by these greater Himalayan sequence rocks. So these are high-grade metamorphic rocks and leucogranites. And the green symbols here are dominated by lesser Himalayan sequence or Tethyan Himalayan sequence rocks, which are metasediments, low-grade metamorphic rocks, and sedimentary rocks, so presumably weaker. And he sees that when you separate out this population by geology, lithology, you end up with pretty significantly different regressions. So instead of a single regression for the whole data set, he wants to suggest two different KLP values based on lithology. And so that allows, and that's what these values are down here, that allows them to produce a more detailed predicted erosion map incorporating lithology. Now, these in both Kellen's work and in Josh's, this is just an intermediate step. Now he's got to go do interesting things with it. But having this sort of high resolution prediction, I think, is really exciting. Okay. So sort of making a transition here from a bunch of studies where I think hopefully I've convinced you that rocks matter, but it's been a bit unsatisfying. So in the first study, we just looked at qualitative differences in erosion rates in different lithologies. In the second study, Aaron's study, we looked at assigning categorical values 1 through 5 to rocks, which was, really bothers me. And then in Josh's study, we're using an empirical relationship to show that there is a difference, that rocks, behave differently, but we're not really approaching that independently. And so that leads to the can we do a better job with this? And can we independently constrain this rock property KLP? And so that brings me to the work we've been doing in Brazil with Maurizio Barcelos-Haag. So here he is in his field area having a good time in Brazil, and he's located a really excellent place to explore this question of lithologic influence on erosion rates and landscape evolution. And that is the southeast margin of Brazil, where there's basically flood basalts and rhyolites associated with the Etindeca LIP that formed during the breakup of South America and Africa. And it's been essentially inactive since the Cretaceous. And there's certainly lots of things to talk about how escarpments evolve over time and rejuvenation of older topography. But for the purposes of this study, I think we're quite safe in assuming that this region is tectonically quiescent. So tectonics aren't playing a role here. And not much else is either. So here's a zoomed in version just showing the escarpment, and this is a slope map. Here's the geology, so the rhyolites in pink and the basalts in green, and then the yellow is the rocks of the Parana Basin. And you can see it here in a geological cross-section, which is very vertically exaggerated. The orientation of these rocks is actually subhorizontal. And you can see these faint lines here. There are vertical fracture sets throughout the region, but we didn't observe any systematic differences in different lithologies. So bedding orientation and joint orientation and spacing probably matter in erosion, but in this case, we think that it's not a factor because it's the same throughout the area. And other things are the same. So precipitation is flat across the region. There's no significant difference in vegetation. Along strike, river steepness, and hill slope as well. They're all flat. So the only thing that's significantly varying across the region is the lithology. So in this yellow line, it's hard to see, but you can see that there's an increasing percentage of sedimentary rocks as you go from south to north along this transect. And down here in the bottom are the erosion rates that we measured, and you can see that they're increasing, and they're shown in the black dots here. So quantitative or qualitatively, again, to first order, it looks like not much else is going on, but erosion rates are responding to lithology. So it's a good place to dig into and explore this question a bit more. I'm going to take another pause and talk about method, and that is, how do we think we can independently measure rock strength? So Sklar and Dietrich did a really important study back in 2001 where they experimentally eroded rocks and of different lithologies, and then they tested their tensile strength in the laboratory using the Brazilian splitting test. And they found a good correlation between tensile strength of rocks and erosion rates. And this is the relationship, and there's this exponent here, -2. So erosion rate is proportional to the tensile strength, the -2. Tensile strength, like I said, is measured by this Brazilian splitting test. You can't do it in the field, and it's not easy to do, and it's not easy to do a lot of measurements. But it turns out that tensile strength and compressive strength correlate well. And so we can measure compressive strength in the field and substitute that for tensile strength, and we expect a relationship between that and erosion rate. So measuring compressive strength is relatively straightforward. Oops, sorry, forgot this part. Yeah, so KLP we think is proportional to uniaxial compressive strength to this -2 power. So how do we measure the UCS, or the uniaxial compressive strength? It's pretty straightforward to do that. We use a Schmidt hammer. It's an instrument that's about $1,000 or so. We broke one and just bought a new one, so it's not difficult to get access to it. And it essentially fires a piston at rock, and the harder it bounces back, the stronger the rock. You get a higher rebound value. And then there's a straightforward formula for converting from rebound values to UCS. And then again, we think that relates to KLP, or to rock strength. Okay, so here are some results. So this is Maurizio's measurement from his field area in Brazil of the rhyolite and basalt, those capping units from the LIP, and you can see that they're quite strong. The vesicular units within the basalt are weaker, have lower rebound values and lower UCS, and then the sedimentary units, they decrease in strength depending on their grain size, which is maybe not surprising. So how does this relate to erosion rate? I wanted to come back to Aaron's study where we use the statistical approach. So here's Aaron's data looking at summary statistics for topographic variables. This is Maurizio's results for more or less the same metrics, and you can see they more or less look the same. In general, these variables that capture the extreme values or the ranges of values perform well. KSN doesn't do well for some reason. In terms of the climate variables, we got similar results with NDVI doing a good job in general, and particularly these more extreme values, and in particular, the range of NDVI does well. In Aaron's study, lithology was kind of abysmal, this 0.01 regression, at least when we were doing bivariate analysis. But this is Maurizio's version incorporating our rock strength measurements. And just look at the one here on the right, which is our average basin KLP, and there's a strong positive correlation between erosion rate and the rock strength. So it works well. That's great. And then here's another example of how we can, so we're going to compare predicted erosion rates and measured erosion rates. In the Himalayan study, it was a little bit circular, right? We were constraining KLP and then using it to predict erosion rates, but we were using our measured erosion rates to predict erosion rates. So you can't compare really the predicted and measured erosion rates. But in this case, we're independently determining erosion rate using this equation. So we're feeding in this KLP value that we've independently constrained rainfall and our KSN measurements from the DEM to predict an erosion rate, and then comparing that against measured erosion rates. So here's what it looks like if you assume uniform KLP. It's not great. Here's what it looks like if you build KLP into the analysis. So the regression improves considerably, 0.84. So we can use KLP very well to predict erosion rates, at least in this setting. So that led us to a natural question, which is, I mean, it's not terrible to do Schmidt-Hammer measurements, but do we have to do them at all? So is a granite a granite a granite? So anywhere you go, are you going to get the same strength measurements? And if you do, then maybe you don't need to do it individually. And so that led to Maurizio's next paper, his next work, which is to create a global database. And we decided to call the database Thor because of the hammer. And the stunning graphics. And Maurizio is going to be presenting, he's working on a paper, but he's actually presenting this at AGU. So anybody who's going to be there in December, please stop by and talk to Maurizio directly about this. So the database includes 264 papers, so 264 studies, there's 6,000 sites, and actually 148,000 individual measurements. It well represents rocks at the surface of the Earth. So in gray are abundances of rocks at the surface of the Earth, and green is the Thor database. And down here, we're showing underrepresentation. So we're a little bit overrepresented in carbonate rocks, and we're underrepresented in mixed lithologies, which is not surprising. They tend to be finer bedded, a little bit harder to measure. But in general, we have representative database. And then here's some more ways of looking at it. Here's the lithologies. For some reason, Turkey is overrepresented, but I don't think that's a problem. We have rocks from all sorts of climate zones, and then we have data both from the field and the laboratory. The point of this slide is that it's quite a robust data set. We don't think that there's any significant holes. And so it lets us do some interesting things, both in just looking at rock strength, and then also in terms of using it in landscape evolution studies. So here's the summary of the database. This will be, and maybe is already available as a database, so as a spreadsheet, so you can dig into it in great detail, but this is just the summary. And I'm actually going to simplify it a little bit more so it's easier to see the trends by just showing you the interquartile range for each of these different lithologies. Let's I think see the trends a little bit more easily. So in general, metamorphic and igneous rocks are stronger, more resistant to erosion, and sedimentary rocks are weaker, plus volcaniclastic rocks. And there's some interesting trends in terms of decreasing strength with decreasing metamorphic grade. I turn it around, there's increasing strength with increasing recrystallization, so from limestone to dolostone, and then decreasing strength with decreasing grain size. And Maurizio has gone in and explored this, and there's some surprising results, and it's really quite interesting, but more than I can talk about today. And then back to the question, do we have to measure, is a granite everywhere? So some of these rock types are relatively tightly constrained, and so probably don't require field measurements if you don't want to. Granulite, quartzite, migmatite, granodiorite, basalt, travertine, siltstone, and mudstone. But some of them are quite poorly constrained. So schist, perhaps not surprisingly, carbonate rocks, dolostone and limestone are poorly constrained, perhaps because they have so many facies, boundstone and waxstone and so on. And then conglomerate and shale, heterogeneous and shale is quite hard to measure. So there are two options. One is you can measure these poorly constrained lithologies in the field, and the other option is you can exclude them from your analysis because they are hard to constrain, sometimes even in the field. All right, so that's the database. Now let's put it to use in a couple of cases. The first one that Maurizio looked at was comparing it to this interesting global data set that Ott published a couple of years ago. This is KSN right here. And he has it separated out by tectonically active and inactive regions, and then by major rock type. If we incorporate rock strength, we can do regressions of KSN versus KLP, this bedrock erodibility. And if we build it in, we find that we can get a very good regression in active regions and an even better one in inactive regions. So this is, I talked about scale. This is a successful approach to constraining rock strength at a global scale by using this database and measured KLP values. And then here's another more local application of this data set. So I'm going to show you two studies. The first one is from Maurizio's database from Brazil. This is a bit confusing, but this is a regression of measured versus predicted erosion rates. And because N isn't independently known, he's varying N down here. And the y-axis is the goodness of fit, the R squared. And blue data is measured and predicted erosion rates, but assuming a uniform KLP. And you can see it's not great, but when you incorporate field data, that's the red line, you do better. And when you incorporate rock strength from the Thor database, and this is subtracting the complicated basins, you end up with a very good good performance, an R squared of 0.9 in some cases, some values of N, which is great. And then I wanted to go back to Aaron's database where we had this sort of poor performance for lithology, if you remember from this diagram here. And so the blue line again is not correcting for lithology. The gray line is all of the Thor database, and then the black line is excluding the complicated lithologies. And we can see we go from significantly improve the quality of the regression when we use this KLP measured rock strength in the regression. So it seems to help, considerably. Okay. So I'm not done, but there's a sort of a summary point here. So the first thing is, yes, climate and tectonics, but we need to nestle lithology in there as an important factor to consider. And I'll talk a little bit about next steps. There's lots of work, as we all know, to do in the area of understanding the influence of climate on the landscape. So this is just my opportunity to promote Josh Wolpert's other work, very different from what I presented here, where he did the modeling of landscape, looking at the impact of climate cyclicity on the landscape. So not just spatial variability, but temporal variability. So if you're interested in that, he has a talk at AGU next month. And then in the area of exploring lithology in more detail, Maurizio's continuing to work on this. And particularly, he's got these two really nice transects where he's got extremely detailed measurements of KLP and KSN. And he's going to be looking at how they covary. And then Himani Yadav, who's another PhD student working with me, is working in the Canadian Rockies where the lithology and the conditions are quite different. So she's working on carbonate lithologies, which, as I mentioned from the Thor database, are quite poorly constrained. So she's looking at how facies may relate to carbonate lithologies. So it may help us straighten some of that out. And she's also looking at chemical weathering of carbonate rocks. And then she's also looking at bedding and joint orientation and joint spacing and how that may influence erosion rates. So that wasn't a factor for us in Brazil, but it probably does play a significant part in erosion. So we're going to try to layer that in with her work. And then I wanted to take just another minute or two to talk about uplift rates. So, someone who's more interested on the tectonic side of things, I'm happy to be able to constrain the impact of climate and lithology on the landscape so that we can read the tectonic signal. But it's also useful to be able to independently constrain tectonic uplift rates so that we can then build them back into these regressions to try to understand the relative influence of tectonics, climate, and lithology on the landscape. So how do we try to measure uplift rates? So there's two important studies that have tried to constrain this on a global scale. And Potengman and Bierman used peak ground acceleration, basically this global seismic hazard map, and Ott used this map of horizontal strain. We're assuming that regions of high horizontal strain correspond to vertical uplift. The problem, though, is that, first of all, the spatial resolution is quite coarse compared to the basin scale erosion rates that we're comparing this to. And so the authors both ended up basically asking a yes or no question with these data sets. They were saying, is the region tectonically active or not? So that's not very helpful. It's helpful on a global scale. It's useful to look at, but if we really want to examine this question of tectonic control on landscape evolution, it's not very helpful. So in the study I've been talking about today, Aaron Seagren's, we used fault sinuosity. Other studies have used fault length. And that's essentially looking at actual faults to try to understand what might be going on in the basins through which they transit. That's, I don't know, not a terrible way to do it, but it's also not giving you spatially continuous, it's discrete data, just looking at the fault itself. What if you have a fault that's just outside of your basin? What if you have multiple faults within a basin? And it's not telling you about any gradients in uplift rate, for example, in your basin. So it's a good try, but really not very satisfying. What we really want is continuous data where we can actually do summary statistics and look at variations within watersheds. There's a couple potential ways to do that. One is using other morphometric indicators. So for example, valley floor to width ratio floor width to height ratio might be helpful. Hypsometric integral you can do across the landscape. It's a little bit circular because these are affected by lithology as well, but it does give you continuous data. And then the other promising avenue is using data like geodetic GPS information or leveling data, fault slip rates coupled with a block model that allow you to model uplift rates, or thermochronologic data. So for example, this is a study from the Western Alps using geodetic data to predict uplift rates. And this is Matthew Fox's work on thermochronologic inversion in the Western Alps. And you can see these broadly similar bullseye patterns for spatial uplift. So this kind of data set I think is quite promising for looking at tectonic uplift rates. The problem is you need dense data to be able to do these sorts of inversions with any confidence, and there aren't very many places in the world where this data exists. So trying to do this on a global scale is not something that's going to happen in my lifetime or for a long time. So it's aspirational and maybe very useful at local scales, but not something that we can do on a global scale. Okay, so in summary, I hope you saw that spatial scale matters. It's important to think about the question that you're asking and whether or not it's appropriate at that scale and whether or not your answer may differ. So at larger scales, they're necessarily going to be generalized because they have to omit detail, and particularly tectonic and lithologic detail. So smaller scales allow use of more detailed lithologic and tectonic data. And at least in the studies I presented here, we found that those effects of lithology and active faults are more apparent at the smaller scale. Precipitation seems to be more influential on larger scales, which makes sense because it can't change on a dime, right? When you cross a fault, you change lithology and you change uplift rate, whereas precipitation gets smeared over a larger area. In terms of climate, I didn't make much of a point of it, but it seems like vegetation matters in erosion rates is maybe better than precipitation at capturing what's going on. And then lithology, lots of points here. It matters for erosion rates and topographic metrics. Compressive strength seems to measure rock resistance to erosion, so we can independently measure KLP, and we can use measured KLP to better predict erosion rates or independently predict erosion rates. And then our global database, Thor, provides measurements, and it's really interesting. I think, quite a valuable resource for the community. And then in terms of tectonics, incorporating lithology and climate, hopefully we can better isolate tectonic signals, but we also need better ways to make these measurements. And that's something I'm very excited about doing, in the next couple of years, I hope. So with that, I just wanted to say thank you to everybody, and in particular, anybody who's in the US today. It's kind of a major holiday, which I forgot about when we were scheduling this. But thanks for getting up early and making time on this, on this big holiday. And thanks to everyone else for being here as well.
Thank you very much, Lindsay, for this talk. It was really, really interesting. And I hope it's not a holiday in Canada as well.
No, just why I forgot. we had Thanksgiving, but it's in October.
Okay. The chat is open for questions. Everyone, please write your questions. I think it's a very interesting talk, so we'll have a few, at least, I hope. For me, I already have some. When you were constraining KLP, depending on the lithologies, I was wondering what accuracy do you think you will achieve? Because right now there's of course a lot of factors coming in, and I was just thinking about studies I read about, for example, the upstream lithologies that would create sediment, and depending on the rock strength of the sediment, you would have different erosion rates in the downstream lithologies. Do you think you could achieve this kind of resolution with this kind of method?
Yeah, I mean, there's two questions there. Right? There's one is, can you actually just measure, if you have just a block of rock, can you accurately measure the strength of that rock, right? The resistance to erosion of that bare piece of rock. And yeah, I think that you can. Better for some lithologies like granite, poor for fine-grained sedimentary rocks or schists or whatever. But that's sort of a separate question. And that one I think is fairly easy to constrain. But again, we've chose a very special place in Brazil where there wasn't a lot going on, and so we were able to find that just measuring rock strength did accurately tell us what was going on in the landscape. But yeah, there's some confounding factors. One is, I mentioned earlier, but joint spacing, right? So if you've got very highly fractured rock, a granite that's highly fractured versus one that's intact is going to erode very differently. Constraining that is hard. There's I think it's called RMS, but there's ways of doing that, and I think engineers use those techniques more. But doing that in across a watershed is very difficult. You could do it in an outcrop, but how do you sort of apply that across the landscape? So Himani's work, I think that we're going to just basically look at bedding, because that is something that you can measure, using geological maps or satellite imagery. You can measure what the bedding orientation is pretty well. And so we're looking at how erosion rates vary depending on the orientation of bedding in the basin. Looking at joints is different. And then you also asked, mentioned the idea of, I think, the tools that end up in the stream. So if you have a resistant rock and it's contributing a bunch of material to, so I'm thinking there's Joel Johnson did some work years ago in the Henry Mountains where they have these stalks of diabase or something like that surrounded by sedimentary rocks, and those tools traveling down the and eroding efficiently into the sedimentary rock was important. And in Maurizio's landscape, it's the same sort of thing. These basaltic blocks influence erosion downstream. So we didn't sort of see that showing up in the data, but we actually have an undergrad student working on that problem right now. So yeah, interesting. I don't know. I mean, there's first order. So I think to first order that rock strength does well, but then there's all these complicating factors that we can call noise, or maybe someday we can kind of sort them out and constrain those better as well.
That would be super cool. And we have Brian, thank you for the answer. We have Brian Whaley that says, thanks for the talk. That was very interesting. And he's asking if the fractures, but I think you already answered part of that. If the fracture density and RQD would be better estimates of rock strength, which normally fractures in the shear, like when you were comparing compressive strength via air values and Schmidt hammer. I don't know if that talks to you.
I have to read it.
Yeah, sorry.
That's fine. Yeah, I think that is what it just addressed that a little bit. But yeah, those are, I don't know if they're better estimates or not. I don't know. That's a good question. I mean, maybe we need a study area that allows us to isolate that factor on the landscape. Like I said, in Brazil, we were able to get rid of it, and we got rid of it because we didn't want to deal with it because it is probably quite complicating. So again, we did pretty well with just looking at rock strength. So, suggests maybe that these other factors aren't as important, but it might have just been that particular landscape. Yeah.
Yeah, then I can just take the next question, which is by Surya there, who says that in summary, the plot for the Thor database, a lot of the rocks listed show a lot of overlap in the ranges of compressive strength. So at which scale do you think distinguishing between lithologies becomes important?
Oh, that's a really interesting question. Yeah, so the tails on that data set were quite long. And we haven't really dealt with those. I mean, when we're doing when I'm showing these plots of KLP, we were just using the mean value. And I just said earlier that means aren't great, right? But we were using the mean value, but we weren't really considering the tails or the uncertainty on the data. So maybe there's a way to build that in. And yeah, I get the question, like if there's so much overlap, does it matter, what the rock strength is? And I suppose in some lithologies, I don't know. It's a statistical answer, I'm sure, and I don't really know what the answer to that is. But I think the tails were a little bit misleading. I think if you really look at like the interquartile range or the 95th percentile, right, like it's actually relatively tighter. That was the boxes that I put on top, and I think that there is significant difference. And again, I guess it's maybe, does it show up in the landscape? Like, if it looks like it makes a difference, then it probably, the differences in the different rock types probably are significant. But yeah, I like the getting back to the spatial scale. When you zoom out, maybe, it doesn't matter whether you're looking at two different rock types, because at that resolution, the differences are insignificant. That's an interesting question.
We also have a question from Kristen Cook, who asked if it would be useful to add something to a metric to see if topographic stress could be one of the components responsible for KLP.
I'm not sure what you mean, Kristen, by topographic stress.
Like when you have like the gravitational stress and then the tectonic stress and
I see.
Yeah.
And maybe informing some of well, and another thing something that actually Himani is looking at is proximity to fault. So if you're close to a fault, the rocks may be more fractured, or if you're sort of being transported over through a flexural fault bend fold or something like that, you may be producing fractures. So you may be able to relate fracture density to the structural geology in some way. Or yeah, through topographic stress. Sure. I mean, maybe that's a way to get at so I was saying, you can look at fracture density in an outcrop, but translating it to the watershed upstream of that outcrop is hard. But maybe if you can look at proximity to faults or to other sorts of structures or things like, I guess, topographic stress. I need to brush up on that. Okay, thanks for the reference, Kristen. So I'm not sure, but maybe that's a way to sort of generalize or look at fracturing across the landscape in a more sophisticated way. Yeah.
So far we have no more questions, and I think like what Kristen Cook was saying is interesting, because I haven't seen so much anything like what Sergey Moon was doing in any landscape evolution modeling or any landscape evolution understanding analysis, but that's maybe me. Yeah, so far, do you think there could be any way of replacing the Schmidt hammer with something even more simple, so that we could, I don't know, it's a dumb question, but have some people like citizen science approach or something?
Oh.
Because right now it's
No,
still
I don't know. Well, my intuition was just like, because you can hear when the Schmidt hammer rebounds, like you can tell when it's sort of flat because there's a fracture behind it versus when you've got a really hard rock, it kind of rings. So like, the idea of I forget what it is, like the relative weathering just by striking a rock with a hammer and listening to how it sounds, which is very, very qualitative. So probably not something we should employ. So I'm not aware of a simpler tool than just the Schmidt hammer, but I do like that idea. And then again, if there are rocks that are well constrained, then you don't have to measure those specifically, in the field.
Okay, very well. Then I think we can wrap up now because I don't see any other questions so far. Thank you so much for the talk. It was really interesting.
Good.